Hepinize merhaba arkadaşlar. Bugün sizlerle beraber hiçbir şey yapmayacağız. Gerçekten bir tane intro izleyelim şimdi. Bir dakika şöyle açalım. Tamam arkadaşlar. Şimdi ben gideceğim arkadaşlar. Size video olsun diye video çekeyim dedim. Şöyle şunlardan açalım arkadaşlar size. Oh, güzelmiş. Bu güzeldir arkadaşlar. Şimdi şöyle yapalım arkadaşlar. Çok da güzel size. Arkadan da ses olsun diye şunu açalım. Şöyle yapalım arkadaşlar. Hadi görüşürüz arkadaşlar. Ben gidiyorum.
So in set, a monoid is, as we know, a monoid is given by structure. So you might remember a monoid is like a group without the inverse. We have the identity and we have the multiplication. So it's a structure where X is a set. E is an element of X. The multiplication operation is a function from product of X with itself to X. It's a two-argument function on X. And it satisfies some equations. So the equations are that the multiplication is associative. And that the unit is a left and right unit for multiplication. So it's a right unit, and it's also a left unit. So these are two equations. And of course, this is, we don't normally write it, but we mean for all x, y, z, and for all x. And the idea is we can ask, if we've got a category and we've got finite products on the category, we can actually express this property of an object of the category together with two operations purely in terms of that structure. Maybe almost want to move this line a little bit to the left. Let's do that, otherwise it's going to annoy me. So in a category C with finite products, a monoid, I should have underlined monoid because this is a definition. A monoid is, well, the idea is it's not an element of the category, just like a monoid is not an element of the set of the category of sets. It's a structure built from an object of the category of sets together with some additional data, an element and a map. So we're going to build a similar structure using similar data, but data from the category C rather than from the category of sets. So it's a triple, just as before. An X, what did I put next? A multiplication operation and an E, where, so now, well, X is not going to be a set, it's of course going to be an object of the category. Well, we don't have functions, but we do have maps, and it's pretty obvious that when we have a 2-argument function from x squared to x, we're going to replace that. We've got the finite product structure, so we're going to replace that with a map from x times x to x. So at some point in my notes, I realized that choosing x for the underlying set and then using the product operation meant I'm getting at some point going to have large diagrams where x and product occurs all over the place, and hopefully I'll try to keep the product small and the x large, but it might have been better to have chosen a different letter just to separate things, but anyway, hopefully it's going to be clear. So so we have multiplication, the operation is given as a map, and now of course x is not a set, it's an object, so we don't have elements in the object, but we replace the idea of element as an element of x with, well, we have finite products, so we've got a terminal object. Just like in sets, the elements are in one-to-one correspondence with functions from a terminal object, which is a singleton set, into the set x. So we can replace having an element with a function from the terminal object. Satisfying. And we want to express these laws using the finite product structure. And there's a kind of recipe by which one does that. So if you've got a law with 3 variables, well, 3 variables are ranging over all possible triples of things, x times x, y, z. So we're basically looking at 2 different functions here, defined on x on the object on the set x cubed, on triples of things. We've got a finite product, so we've got x times x times x. That's a 3-fold product of x, a 3-fold power of x. Just for future convenience, though it's really the same thing, I'm going to write my 3-fold product as an iterated binary product. So we're going to say, so this first diagram is going to say, if we do this multiplication, then that's the same as doing this multiplication. So if we've got a binary product like this, so we've got little x, little y, little z from here, it's easy to do the multiplication on the right-hand side, so this y times z, because that's just apply the dot operation on the right-hand side. Remember, we have the product functor on maps, so we're producting the identity function, the identity morphism with the product operation. So this takes us to x times x, and we can apply the multiplication again. That takes us to x. So this gives us the left-hand side of this equation, and we want this to be the same as the right-hand side. So to get the right-hand side, we need to rearrange this. We want to put the first and second component together. So we can do that by projecting the first component into here, projecting this component into here, this component into here. But we can also remember that we saw that categories with the finite products were examples of monoidal structure, we have the associated, and what I just said is exactly the associativity map of the monoidal structure. So we can use the associativity map for the finite product to take us from here to here. And now we multiply, we want to do x times y first, which is x times y first, which is the multiplication. So we product that with the identity map on the right, that takes us to x times x, and then the multiplication here. So this is associativity. And these diagrams are expressed in a similar way. We've got two equations there, all in one variable. So our variable with the value of that is being sourced in just the object x itself, and then the variable x is just given by the identity function, and we want to consider that times the unit and the unit times that. So to get that times the unit, we want to go from x to, if we're putting the unit on the right, we're going to go to x times 1, and then we can do the identity of x times the E map, the x times x, and then we come back along the multiplication map here. So this is giving us x multiplied, little x multiplied by E. So what's this map here? Well, it's the it's given by a pair of maps. The identity on the left takes us onto the left component, and the unique map to the terminal object to the right component. But once again, this is a map that's part of the monoidal structure. Remember, the monoidal structure, if we view product as a tensor product in a monoidal structure, the terminal object is the unit of the monoidal structure, and we had this lambda and rho maps that were isomorphisms. I've actually realized how to remember which one is which. Lambda stands for left and rho stands for right. And the right is that you put the unit on the right. So the map in this direction from x times 1 to x would be rho, and this is rho to the minus 1 of x. And this states this equality, and the other equality is you simply put the unit on the right. So we go along lambda to the minus 1 to 1 times x, E times the identity on x, to x times x, and the multiplication in the other direction. Okay, so that is the notion of a monoid in a monoidal category. And sort of natural things hold. So for example, for a monoid in sets, we can observe that E is uniquely determined by the multiplication. So we have a monoid, and an E and these identities hold, well, which they need to because it's a monoid, then there's only one E that works. But that's easy to show. And similarly here, if we have a monoid structure, which means these diagrams hold, we can again show that E, just in the generality of a category with finite products, E is uniquely determined by the map E, the unit map E, is uniquely determined by the multiplication map. That's a little exercise for you to show that at the level of a category with finite products.
Sorry, I have a question. So,
yes.
Satisfying these graphs to you.
Sorry, yeah, satisfying means exactly these diagrams commute. Sorry, I should have said that. Yes.
Maybe you didn't.
Yeah. Sorry?
Maybe you did say.
No, I didn't, but that's what I meant. And it's good. So, I mean, really stylistically, one should really say such that these diagrams commute, but it always, that it's assumed if ever I'm saying such that something different from the diagrams commute, I'll say that explicitly. So the sort of default assumption is, the diagrams commute. So this was associativity in these two. So let's put that blue bit out of the way. These ones are the unit laws or the identity laws. So that's the notion of a monoid. Related to that, of course, one has the notion of homomorphism between monoids. So a homomorphism between monoids is a function, well, let's give ourselves two monoids, so x, bullet, or dot, or whatever, and e, and so we're going to, from that to x prime, dot prime, and e prime. So homomorphism is a function, as you know, h from x to x prime, such that h preserves multiplication, and h preserves the identity. And once again, the notion of I'm going to use the right-hand board, right-hand panel. So once again, the notion of homomorphism can be expressed in a category with finite products. So a homomorphism between, well, from a monoid x bullet e to another, I won't say another, but to x prime, bullet prime, e prime in C. Let's say of monoids from, just to be clear that both things are monoids.
So, sorry, Alex, the board is just a bit blue, or the camera is blue.
It's gone out of focus, has it? So once again, this can perfectly well be expressed very simply by diagrams. I'm going to be a bit quicker this time. So it's given by, so instead of a function from the set x to x prime, we simply have a map from the object x to the map to the object x prime, such that it preserves the multiplication and it preserves the unit. So preserving the multiplication is if you start off in x times x, so we've got a little x and a little y, we multiply them together, we get the result of multiplying them together, and we apply h to it. That's the same thing as, so that's the left-hand side of our preserving multiplication equation over on the other board. That's the same thing as applying h to the variable little x and the variable little y. So to each of them, then we get back into the product, and here we apply, yes, we need primes there, thank you. And here we apply our multiplication in the x prime monoid. And we also want to preserve the identity element, and that's an absolutely obvious diagram, which is that h makes that triangle commute. And unsurprisingly, just as in the case of sets, if we can now make a category in which the objects of the category are the monoids in C, and the morphisms of the category are the monoid homomorphisms in C, and that's a category that we've constructed from the category where are we? From the category C. So this is another one of our constructions on categories. It's a little bit more elaborate than the construction we have of the other constructions we've seen on the categories, or many of them. So mon sub C is the category whose objects are monoids in C. I'll just write so the category of monoid in C and whose morphisms are homomorphisms. I'll just say the category of monoids in C and homomorphisms as maps. I'm not underlining it because what I'm tending to do is underlining, which would be correspond to if we were writing in LaTeX, writing the names in bold. I'm underlining those concrete categories of sets and set-like structures whose morphism, the things like set monoids. So I would underline monoids, the monoids constructed from sets. But here, this is an abstract construction of a category based on the category C. So I'm not underlining the name. Okay, so that's the notion of monoid. So let's extend this to groups. There aren't really any surprises. I should. But let's just check we can do it. So I'll keep the monoid equations up. So again, in the category of sets, what we're used to, we know that a group is given by a set with a multiplication in a unit, an identity, where, well, we can now say, because we've got these monoid laws, we can say it's a monoid. And with the additional property that every element has an inverse. And for every x, there exists, so that for every element little x in x, there exists what we'll call little x to the -1 belonging to x, such that it's both a left and right inverse for x. So x times x to the -1, that's a right inverse, is the identity element, which is the same as x to the -1 times x, it's a left inverse. Okay, so what do we do in the category? So in C with finite products, we're carrying on, and I know I need to move the camera. To brackets, a group is a monoid x. But what? We can't now say for every little x there exists an x to the -1 because we don't have elements. But of course we use the observation that we have in sets. But we're going to make use of very simple observation that x to the -1 is uniquely determined by the above. So we have a function that takes, we have a function, in fact, that takes every element of the group to its inverse, obviously. So, you have the inverse finding function on the group. And so it's kind of obvious what we do. We're going to ask for such an inverse finding morphism to exist. Now, sometimes people put this as part of the structure. You can do. You don't need to, for a reason we'll find out in a moment. So for me, I'm going to take the monoid as the structure, and it's such that there exists a map from X to itself, which I'm going to call dash to the -1. Better to just give it a letter I or something like that, but anyway, just to be suggestive, I'm going to call it that, such that, and we now want to, the point is we view this as a bit of extra structure that's finding the inverse for the elements, and we want to express the left and right identity laws that we had here. So I'm going to put them in the same order. So we've now got an equation in one variable, so we're going to consider it as a map from X to X. And the middle thing is the element E. So what's the element E? Well, we view this, we kind of view this as an expression in the variable X that doesn't use the variable X. So we first go along the unique map to the terminal object, and then we go along the E element to X. So just like this is, because this is the constant expression that's always the identity object. And in the other direction, well, so not the other directions, but to give the left and right properties. So which one did I have? I'll put them in the same order. So the left one, we want to say that if we take an element little x, we multiply it by its own inverse. So to do that, we need to copy the element little x, and we can do that by going along the diagonal map from x to x times x. So that's the map whose components are the identities there. And here we go along. So this gives us, we take the variable little x to the pair little x, we keep little x the same, and we use the product with the inverse map here. So this takes us back to little x, and then we multiply. Okay. And in the other direction, we use the diagonal map. It's traditional to write the diagonal map associated with the product using a capital delta. So I'm going to do that here, x times x. So here we just put the inverse on the left side instead. So here we have multiplication like that. So let's replace that with the delta. So delta is the map, the diagonal map from x to x times x. So that's the pair 1x, 1x of identities. So now we have the notion of a group with, let's try again. We now have the notion of a group in a category C with finite products. I forgot to make the observation, which I should have done, the map. So just as inverses are uniquely determined in sets, the inverse map is uniquely determined. Again, it's an exercise to prove that this holds in the general setting of a category with finite products. And Again, we have the notion of a homomorphism of groups. What's a homomorphism of groups? Well, we know what's a homomorphism between groups in the ordinary set theoretic sense of groups is. So again, it's a, I won't bother writing the definitions. Again, it's the set theoretic definitions. Again, it's a function from the group from the set X to the set X prime that preserves multiplication, preserves the identity element, and preserves inverses. But of course, as you probably know, with a group, you only need to preserve multiplication. You've got a function between groups. As long as you preserve multiplication, it automatically preserves inverses and it also preserves the identity element. So homomorphism of groups is simply a monoid homomorphism, if we like. So such an H automatically preserves the inverse function, the inverse morphism, sorry. So i.e., what we mean by that is so the morphism H from X to X prime maps the inverse function on X to the uniquely determined inverse function. Let's call it -1 prime or something. So that automatically commutes, and the point that once you've got groups on both sides, or I mean, whenever you've got a monoid homomorphism to a group on the right, then preserving multiplication is enough for the identity to be preserved. So this condition, preserving identities, is redundant. Okay. So going back, and we'll follow the. Well, actually, it doesn't matter about that, but the logical structure is taking us back to here. So I'm going to write group sub C for the category of groups in C and homomorphisms. And the way we've defined it, group sub C is a full subcategory of, so category of groups in C is a full subcategory of the category of monoids in C. So full subcategory, I don't know if I used this terminology before. What it means is a subcategory that's determined just by singling out a collection of objects from here. So we look at those monoids that happen to be groups, and we consider the category on those objects that has the same Hom sets as in the category of monoids. So the full sub, it's full because the inclusion function is, the inclusion functor is full. Okay, the full definition will be in the notes. Okay, so we have the notion of group in monoid and group in a category with finite products. So much more general than the category of sets. So is this useful in mathematics? Well, it is indeed. Such things occur frequently in maths. So I'm just going to give a short list of examples. So of course, group subset, these are just groups in set. This is the usual the usual category of groups and homomorphisms. Homomorphisms. So the category we were calling group underlined. So things become more interesting if one looks at other base categories. So groups in the category of topological spaces is exactly, so the group in the category of topological spaces is exactly what's known as a topological group. So a topological group is a group whose underlying set comes together, has a topological space structure on it, such that the multiplication operation is jointly continuous and the inverse operation is continuous. And the multiplication operation being jointly continuous is the same thing as saying it's continuous with respect to the product topology. Because the product structure in the category of topological spaces automatically finds the product topology for us, it kind of gives us, so when you see the definition of a topological group for the first time, it's a nice definition. You can sort of understand how the components fit nicely together. But still, you might think there could be other variations on how one might define it, and it's not clear why you ask for joint continuity, for example, and you might have various questions about it. This gives a sort of good answer. So this description of it shows that the notion of topological group has a canonical status. If you accept the category of topological spaces, we have the general notion of a group object in the category. It forces the notion of topological group upon us. Topological groups are really nice things. I mean, so a slightly surprising fact about them is that if you have a topological group structure on a topological space, that space is automatically Hausdorff. Even if you start off with, just needs to be topological space a priori for the definition to make sense. So that's something that's kind of nice to verify, if you like, looking at such things. So anyway, so we have the category of topological groups and continuous homomorphisms between them, which is the natural notion of morphism between topological groups. And then there was a bit of discussion about this in a previous lecture. So if we take a category which I'll call man, of manifolds, and here by a manifold I mean a differentiable manifold, and the morphisms here are going to be the smooth maps, then the group, but we want to look at, so that's the category, so the groups in the category of manifolds this is the category of Lie groups. So you have differentiable manifolds and smooth maps between them of Lie groups and smooth homomorphisms. But I meant to look at some reputable reference to remind myself exactly what a Lie group is, because actually differentiable manifolds and smooth maps, there are various different strengths of definitions you take, depending on how many times you want to be able to differentiate things in order to get the smooth structure. So one such category would be where where you've got manifolds where the sort of overlap things are just differentiable once, and the smooth maps would then just need to preserve, would just need to be once differentiable. But otherwise you could take another natural one would be infinitely differentiable. And I'm not quite sure what the usual base category here is for defining, so probably somebody else knows this. But anyway, with the appropriate category of smooth manifolds, this is true. Okay, so, and there are other nice mathematical examples too. Okay, so we've got groups and monoids. I wonder, did anybody notice there's some sort of fundamental sense in which monoids are more general than what we're doing now, that groups are not? So I'm going to generalize monoids in the next part beyond category with finite products. But we can't do that with groups. Can anyone see what I'm hinting at?
Instead of products, use a monoidal structure.
Okay, so here we can use a monoidal structure for the definition of monoid, because we notice, and I was kind of careful that I did this as we went along, that all the maps we've used here are ones that only involve the monoidal structure of products. And why can't we do that in groups?
Or the delta.
So there's the delta. So that's the diagonal map that doesn't exist in general for a monoidal product, and also for this map to the terminal object. That also you don't have a map into the unit for a monoidal product. And essentially, what's happening is the equations for a monoid. Every equation of the form is of some expression equals some expression, where you have exactly the same variables on the left and right side. Each variable only occurs once, and they occur in the same order. And when you have algebraic equations of that form, you can use monoidal structure. If you have equations where some variables occur twice, some variables don't occur at all on one side or the other, or you swap the orders of the variables, then you need more than monoidal structure. Actually, swapping the order of variables, you can have a symmetric monoidal structure, will allow you to do that. But to express the properties of a group, you really need a product structure. So we're going to start next time by generalizing monoids to categories with monoidal structure. And in fact, the definition is kind of immediate now, so I'm going to write it on the board so as not to waste lecture time during the break, and then we'll start again from there. Okay, I'm going to pause for the break. Okay, so during the break, I changed the definition of monoid in a category. I generalized it from a category with finite products into generally a monoid in a category with monoidal structure. The definition, it basically remains exactly the same. You know, I'm just replacing the product with the tensor and the terminal object with the unit I of the tensor, or the identity I of the tensor. You do the same thing with the notion of homomorphism, which also makes complete sense in a category with monoidal structure. And so we have a general notion, general derived category of the category of monoids in C. So is this generalization useful? Yes, and I want to discuss just a few examples of how it's useful. So the main running example I've been using in this course for category with monoidal structure, with a tensor that behaves very differently from a product or a coproduct, is vector spaces. So let's have a look at what a monoid with respect to the tensor product in the category of vector spaces is. So a monoid in category of vector spaces over a field K. Well, it's given by, let's keep the same letters, so it's given by an X, a multiplication, and E, where multiplication goes from the tensor product on X to X, and the E is a map from the unit of the tensor, which is just the field K itself, into X. These are, of course, linear maps. So a linear map from the field to itself is simply corresponds to an element of the field, namely where we map 1 to here. I'm going to call this E. So let's put it like this. So E corresponds to an identified element of X where we're mapping 1 to. So I'm just going to call that 1 underlined. The image of 1 belongs to X. So 1 underlined equals E1. And this is a map out of the tensor, so of course it's a bilinear function. X times X corresponds to a bilinear function from the product of X with itself into X. So let's write out what it means to be bilinear. I mean, you know, this is easy, but there's a reason that I'm doing it. So bilinearity means that if we consider kx and multiply that by some little k from the field k, kx and multiply that by y, we get little kx multiplied by y. Well, let's actually, rather than x and y, I'm going to use I'm going to use a kind of vector notation just to make it. So k times u multiplied by b is k of u multiplied by b. U multiplied by k of b is k of u multiplied by b. U plus v multiplied by w is uw plus v of w. I don't really know if it's really worth writing everything out. Anyway, this is bilinearity. And this is, so these are just saying that, well, it's bilinearity. And then we have the monoid laws. So the monoid laws are let's put them in this order. And that okay, and then, so this is the monoid laws. The reason for writing everything out in full is, you know, it's coming out again automatically from the category theoretic definition. Hopefully some of you have met this concept before. This is a very widespread concept in algebra, which is the notion of what's called an associative algebra over the field K. So an associative algebra has the vector space structure together with a multiplication that's associative, and you have the expected distributivity laws over between the multiplication and addition of vectors. So the kind of thing that, you know, classic examples of this would be like square matrices over K or something like that, where you've got an associative multiplication that interacts in the appropriate way with the addition operation. So monoids are exactly associative algebras. Associative algebras. So another example, which I'll leave it, well, two examples, which I'm going to leave you to think about. The first one, I'll tell you what the answer is. So in the category of categories, but actually now I'm going to look at monoids with respect to the product structure rather than a monoidal product structure. The monoids are exactly. Does anyone have an idea what a monoid in the category of categories should be? So monoid. So now we're using the product structure. So you've got a category. You've got a functor from C times C to C. You've got this will give us this will be the terminal category, and this will give us an object of the category, satisfying some appropriate equations. Has anyone got an idea what that's going to be?
Category with monoidal structure.
Almost very good. So yeah, I mean that's correct, but are exactly categories with monoidal structure. But it's a bit more than that. Well, this is a lot more than that. It's strict monoidal structure. So because we've got equations here, strict monoidal structure, you might remember I did introduce it 2 or 3 lectures ago. Strict monoidal structure is one in which all the coherence maps for the monoidal structure are all identity maps. Okay. So of course, the level of categories with strict.
Sorry, I think it's the camera.
The board, yeah, the camera, sorry. The level of categories with strict monoidal structure is not so natural, because in categories, it's very natural to ask for these sort of coherent isomorphisms between things. And really what's happening here is you could say that the notion of algebra with equations is not really appropriate for defining categories. You want some more subtle 2-dimensional notion there. So it's possible to do that. There's actually another approach to obtaining the notion of a category with monoidal structure as an example of a more general category theoretic concept, which is categories with monoidal structure are exactly one object but by categories. So that's I haven't applied categories like a generalization of 2 categories. So anyway, I'm just, telling you there are sort of different directions one might look at. So this is in CAT, the category of categories. So there was one other interesting. So here we've got categories with strict monoidal structure. I did actually 2 lectures ago give you an example of a category with strict monoidal structure, which is the category of endofunctors on the category, where the monoidal structure is composition of endofunctors. And this week's weekly puzzle is the following. Week 9 puzzle, which is what are the monoids in the category of endofunctors on C. So functors from C to itself in the strict monoidal category on C, as defined 2 or 3 weeks ago, where the monoidal structure is composition. And in this case, this is a slightly different puzzle in that I'm not expecting it. So some of these puzzles were look at this category theoretic design concept, defined concept, and try to recognize it as something you will have already met in mathematics. Except for those of you who know the relevant category theory, you will have not met this notion before in mathematics. So the task this time is not to recognize it as something you already know, but rather to write out what the structure of a monoid is in the category of endofunctors with this monoidal structure in direct terms. So such a monoid is an endofunctor together with some additional structure over it expressed using natural transformations. And what exactly are the conditions that correspond to that being a monoid? Okay, so the task is to give a definition in terms of an endofunctor plus natural transformations satisfying some properties. Okay. Right. So where I want to go from here is just give you, essentially I want to give you a little bit more of a flavor of the kinds of constructions one can do in this level of generality of algebraic structures and similar things defined internally, as it's called, with respect to a given ambient category that we choose that has sufficient structure to make the internal definition. And what kind of structure we can define depend on how much structure we assume on the category, of course. You see, one reason one works in mathematics with the background category of sets is the background category of sets has a huge amount of structure, so using that one can define lots and lots of stuff. In general, the category will not have as much structure as the category of sets, and it's interesting to know what we can do with whatever amount of structure we've got. So we're going to have sort of various interesting levels of structure on C. On C. So the weakest one is going to be what we use to define monoids. So monoidal structure. And using monoidal structure, we can define monoids and certain other algebraic structures. I'm just going to put ... and I'm not going to write it down, but it's written down a bit more in the notes. But certain other algebraic structures that we can define using equations between operations, where, as I've already said, the equations always have exactly the same variables on the left-hand side of the equalities. Each variable occurs only once on the left and right side of the equality, and the variables occur in the same order on the left side and right side of the equality. Like in the associativity operation, you have x, y, z, each appearing once in the same order on both sides of the equality. Then there's symmetric monoidal structure. That allows us to move variables around. We still need to have the same variables on each occurring once on each side, but they don't need to occur in the same order. So here we could define, in this structure, we could define commutative monoids, because we can also express the equation that x multiplied by y is y multiplied by x. Let's put ... because there are some other things. Then we have finite products, where we've now got copying. That's we're allowed to duplicate variables because we've got the diagonal, and we're allowed to have different variables on each side because we're allowed to get rid of variables using the map to the terminal object. And so with finite products, we can basically express arbitrary algebraic structures let's say equationally defined algebraic structures. Involving total operations, but where the operations we have are total functions. And then beyond this, we might ask for finite limits. So we're also finite products plus equalizers or plus pullbacks, if you like. And this gives us more generality. E.g., allowing for some partially defined operations. We haven't yet seen an example of this. And I want to, for the rest of the lecture, basically just, there's a whole general theory here, but, that would take us too far afield in this course to develop the general theory. So I just want to illustrate the kind of things we can do using one further example for finite products and one example for finite limits. So the finite products, I'm going to look at, we've looked at groups involving finite products. I'm going to look at what are called, so you call the group defined in a category, a group object in a category, an internal group to the category. So we're talking about internal algebraic objects in the category. So a little bit more complicated than groups would be rings. And once you have rings, very natural notion associated with a ring is module. So I'm going to look at rings and modules and so show how finite products allow us to do those relative to an arbitrary category of finite products. And an example of finite limit, of what we need finite limits for, I'm going to look at defining the notion of a category itself. So that leads us to the notion of an internal, what is a category? An ordinary category, a small category is a category internal to the category of sets. What's a category internal to some other category C? So we're going to look at internal categories. And essentially, in all cases, one way of looking at the task is we need to, normally when we make definitions in mathematics, we use set theory to define it, and that, as I've already said, gives us a lot of power. We've got a huge vocabulary of tools we can use in set theory that we can make use of to define our structures. When we're trying to do things internally in a category, we have to be very parsimonious about it. We have to be, we only have certain constructions available. We have to check that we can reformulate the ordinary definitions using only the structure we have at hand. So I'm going to do that for rings and modules using finite products and for internal categories, but for categories using finite limits. What's the parsimonious mean? Being economical in how you express things.
So like frugal?
Sort of. I mean, frugal is careful with money, really. Parsimonious, yeah, but it's probably, if you look at synonyms of frugal and parsimonious, you probably get, you probably get them linked. So parsimonious, I think, is frugal is basically being parsimonious with money. Even for a native language speaker, it's very hard to actually find a dictionary definition of a word on the fly, and I might be completely wrong. So you should double check such things. I vouch for the mathematics on this course, but I don't vouch. And I vouch for the English in the sense that what I say should be understandable by an English speaker. But there may be, language is a complicated thing, so there may be lapses occasionally. Right, so rings. And I'm not going to give, the basic thing is every such structure is going to be given by some maps, an object, some maps, and some equations expressed as diagrams. But we did this very thoroughly for groups. If I was going to write out all